Okay, right. Is it working? I think it is. Right, so I had a mishap yesterday. I just want to explain. I was going to do a test yesterday, but my mini drill died on me, and I had to cut the damn thing open with the with my hacksaw because this thing was glued together. I mean, it's like them sealed units you get where you can't find the seam. Anyway, I took the damn thing apart, cut it open. I actually used my ABS plastic to stick it back together again afterwards, but you won't believe what had gone wrong. The noise suppression disc capacitor across the motor had gone short circuit. So I didn't initially check that. I should have done, but I actually thought it was the motor. I was convinced it was the motor that got shorted. So I took the motor apart, only to find out it was the ceramic disc capacitor, because I only found out after I checked the connections on the carbon brushes by holding them apart with my fingers and checking with a meter. I thought, well, there's still a short there. How can there be a short? It's not even connected to the commutator. And then I realised it was the disc capacitor. Ugh, I hate it when these things get you, like catch you out like that. So anyway, I sorted my drill out. It works again. Oops. Should we try this? There we go. So that works. So I couldn't run this thing. I've got another drill, but it's on my it's on my 3D printed cutting table sort of thing. I wasn't going to start messing about taking that off because it's covered in graphite. Not graphite. It's covered in ferrite, black powder dust and all that. So I get it all on my hands. I hate it. So I left it. Anyway, I got this one sorted, the drill, and I wanted to show you the improvements. I want to be quick really because I'm kind of tired. I went to sleep about 5 hours ago. I didn't get my full sleep, and I just couldn't sleep for some reason. I just tossed and turned, and I kept waking up, and I don't know why. Anyway, I've got my oscilloscope hooked up. I want to show you the waveforms because we haven't done that yet, have we? And so let me just put the phone in the stand that I made. I'm hoping it doesn't droop on me. I'm going to have to sort this out. I really need to sort that out actually. Let's get the phone in. I'm hoping that I can get it close and without it drooping on me. Maybe you'll be able to see it. Right. Oh, it's probably going to droop down a bit anyway. Right, so we're interested in waveforms. Now, we're only interested in the blue channel because I haven't got anything, the yellow channel's not connected to anything. Right, so we're just watching the blue channel. What we're interested in, RMS voltages when it comes up, and we're also interested in peak-to-peak voltages because it is significantly better than the previous ball configuration. So anyway, I've left the camera over there just a minute while I spin this thing up. Give me a second. I'm just plugging my meter in and everything because I want to get that ready for when I pick the phone up again because I don't want to be doing it with one hand. Okay, right. So I'm going to spin this up now. I hope you can see that. It's not very good, I know. Let me try and get this a bit nearer without it drooping on me. It's drooping on me. Hang on. I'm trying to put the clip on here so it doesn't sag. Ouch! Come on, you bugger. I can't get this on. Sorry about that. Hang on. I think it stopped drooping. Let's see. Let me speed it up again. Right. So you're seeing the waveform now. I need to drop this down in height. I'll take the extension off a minute. It's a lot better balance. Notice it's not glued, it's not even glued to the table, and it hasn't even moved from when I started. Get the base stuck on a minute. Right. Just a minute, get this in the right place. Right. So this thing is not stuck down, look. It's not even moved off its place when I started it. I don't have to hold it, so it's a lot, the balance is great. Now, my meter battery is flat, this thing. So it's not giving me very, I don't know if it's giving me very accurate readings. I think it's, to be honest, it's because the frequency of the pulses, it's not able to register the true voltage or true RMS, so the meter is only giving me point something of a volt, which is obviously not right, because the oscilloscope says that it's about 5 volts actually, peak to peak, or more than that. It's actually 12 volts, isn't it? Yeah, 12 volts peak to peak, and it's about 5 volts RMS. So my meter battery isn't very good, so I don't know if that's got anything to do with it. I want to get this on as well, but the meter isn't giving. Oops, wrong one. I need to pivot that one. Right, let's get this straight. So the voltage is, it's only showing up as half a volt, which is very strange. Actually, don't think the meter's even connected properly. Right, it must be. Let's go to current. Right. It's not connected right now for some reason. Let's try getting this on. Oh, it's nearly stopped actually. Right. Let's get this spinning again. I'm on current right now. Oh, it's not connected. There we go. About 11 milliamps. Nearly. These clips are really useless. Right, so that's current. Okay, time it. I'll have to time it later. So it's about 11 milliamps. And dropping. So I've also been well, I hope you're timing it anyway, because I'll have to do it later myself, because I'm just doing too many things at once here. I'm thinking about designing a new coil system for this this rotary system. I use a folding coil. This is a prototype I was working on, but I need a big one, really big one, a folding coil that will basically wrap around the drum. I don't want to touch it because we're timing it. So I want to have a coil that's shaped like a C shape, or a cup shape that will actually wrap around. That way we'll get a lot better coupling on the steel as it's rotating around, because most of the flux is actually coming around the sides as well as the front. So yeah, anyway, keep timing it. We're nearly there. The current's nearly dropped off now. Notice it's a lot better than the ball system, and I'll explain that in a minute if I can. There's two reasons for that. I can't really show you until it stops. So as I said previously, this basically has static magnets, static coil. The only thing that's moving is the steel coupling on the drum, which is actuating the magnetic field towards the coil and actually moving it partially before it cancels out. Then it comes on the other pole. Alright, get ready with your stopwatch. It'll probably, I don't know if it'll take longer to stop though, because of the amount of increased mass. There's a lot more weight on it now than there was, so it's probably going to take longer to slow down anyway. Stop. Right. Okay, we'll do the same test just with voltage now. So I'm going to go to 2 volt range. I'm going to do the same test with just voltage. I have to hold it while I'm pressing down with this thing, because otherwise it will tip over on me. Okay, start, yeah. So we're on voltage now. Well, remember that's not reading properly because of the pulses. It can't seem to register unless it's 50 hertz or something. I don't get it. The frequency is pretty low actually. I'm actually getting on my oscilloscope, it's around 6 microseconds or something, which is probably why the meter can't read it. Oh, 6 milliseconds, sorry. It's jumping around a bit. I'm getting weird readings on the oscilloscope as well. The frequency is just so high that meter isn't able to respond fast enough on the voltage reading, but it seems to measure current, which is, well, a good thing. Current is current, I mean, but I'm a little bit baffled about why it's not seeing the RMS voltage. We should be getting the RMS on that meter. You can see the gap behind that coil possibly. I don't know if you can or not. Maybe I'm not in the right place. Just moving the camera a bit so we can get a bit of... Oh, there's a gap behind it. That's how big the gap is. Very small gap. Actually, my battery's flat. It's still on volts anyway at the moment, but I'm going to turn the meter off because it's pointless having it on. But it's still, I mean, voltage doesn't really put a load on it anyway. When it actually, I'll wait, it's nearly stopped now. Stop. I think, yeah. Anyway, so interesting. Now, what I was saying earlier, let me get the phone out over here. Find somebody to grab it with. Come out, you bugger. Let's have to get it over here. Yeah. Oh no, I need to push at the front as well. That's it. Right. There's a knack to getting it out of here. Right, I got it out. So, the reason why I was talking about this being more efficient, and there's two reasons why. And the first reason is when we were using the balls, we just had one ball, and the ball would pass the first magnet, then it would pass the second magnet, and carry that flux through to the coil. Well, with this situation, we've got, instead of just two paths where the magnet, when the rotor's in that position, the flux from this magnet is passing through these laminations guided towards this coil. Now when it passes, when it's in the middle, it's cancelled, it's neutralised, there's basically nothing, just both sides are equal, different poles. So that pole and that pole are both conducting equally towards the coil, so it's cancelled, so it dips off. Then it gets to the second magnet, which is this one, which conducts the different pole through these laminations to the coil. Now we're actually getting low power on this between these two. The peak power comes between this one and the next segment, which is this segment here. So this segment is carrying this pole through to the coil. Then we switch where there's no longer a ball in there, so that's a gap, and then we have flux carried from this pole through here to the coil. That's where we get the higher peaks. So I don't know if you noticed on the oscilloscope, but there's two sets of peaks. There's small peaks and there's big peaks. The big peaks are coming between here through here to the coil, and the smaller peaks are from here to here, right? Because this is dipped in the middle, whereas from this point, from here to there is no dip. So we have a pulse from here going through to the coil, and it tapers off. Then this one takes, this is the opposite pole, this takes precedence and pulses the coil, so we get a bigger peak. Whereas with this one, we tend to get a cancellation in the middle, so we get a weaker peak. So anyway, I want to explain that. So yeah, that's it. This was supposed to be a short video, and I've been going for what, 20 minutes. Yeah. Anyway, so I explained it. We did some tests, and we can go back and time it. I could remember there's more mass on this now, so it's going to take longer to stop anyway. So the measurements that we did previously with the balls, the steel balls in there, won't be comparable to this because there's more mass. There's a lot more steel mass in here. This wheel is a lot. You know, probably noticed I've got this really well balanced now. There's very little wobble on it now. It's much better. So there's more improvements to do. I mean, obviously I can design. I mean, these coils weren't designed. These was designed for that thing there. These coils weren't designed for this. So at some point I need to make a coil that's specifically designed for this. Something which can encompass more of the flux around these sections. So I was thinking about either a coil that wraps around and that has a slight fold in it like this, so it can basically fold around the drum to capture that flux more effectively. That's one possibility, or just another flat coil, sorry, two coils. I could effectively put two coils, three coils actually, a coil at the front, a coil on the top, and a coil underneath, which should effectively be the same thing, all wired in series, so that we capture more of that energy as it pulses. So I could in theory use three coils, have one on the side where this one is, and then one. I'd have to make up a mounting system that would hold it above there though, and it would have to be an exact parallel alignment with this one, otherwise it would just cancel out with that one. So, but those are some ideas I was thinking about. Anyway, so I hope you found it interesting. The waveform is definitely interesting for me. I was quite surprised at the voltage. Oh, I've just realised something actually. I just realised something. My probe is on ×1 and my oscilloscope is configured for ×10. Oops, right, so the voltage is not as high as what it was reading on there. We have to divide the voltage by ×10. I just looked and it's on ×1. Yeah, down here. Yeah, these switches keep getting moved. They're so easy to knock the switches. That's probably why I'm getting more voltages on the scope. Okay, so we figured why that was giving higher readings. So at least I managed to do it before the video ended. Otherwise it would have been embarrassing because I would have had to put a comment in the chat. A comment in the description about making a boo-boo. Well, at least I spotted it. Right, so I put that on ×10 now. The important thing is the current it was drawing when we were running it, and how long it takes for this to stop. It's just a question of getting these coils right now to wrap around there to basically capture more of that power coming through. So anyway, I put that back in ×10, and well, we can just do the division on the mathematics. You can just divide it by 10. Instead of ×10, it will be divided by 10. So whatever readings we were getting on the oscilloscope, divide them by 10. Okay, right, that's it. See you later.